Good afternoon, everyone, and welcome to the Julius Rabinowitz Center for Public Policy and Finance 11th Annual Conference. The topic of our conference this year is Evidence to Action, Achieving the Net Zero 2050 Targets. My name is Atif Mia. I'm a professor of economics and finance here at Princeton and also the director of the Julius Rabinowitz Center for Public Policy and Finance. Before we begin with the official proceedings, I want to just go through some basic housekeeping notes. As everyone is aware, this thing is going virtual. We are recording this session, and it will, or it is being live streamed on YouTube as well. The videos of the proceedings will be edited and then made available following the conclusion of this conference. We do welcome everyone's comments and questions throughout the conference. If at any point you have a question or a comment, please feel free to use the chat box, which should be at the bottom of your Zoom window, and you can type in your question and comment in the window. Let me just begin by thanking a number of individuals. It took a few months to put this conference together. I want to thank Kris Gregg, who is a senior research scientist here at Princeton. Simon Levine, he's the James McDonald Distinguished University Professor in Ecology and Evolutionary Biology. Denise Mozerol, Professor of Civil and Environmental Engineering and Public and International Affairs. Michael Oppenheimer, Albert Milbank, Professor of Geosciences, International Affairs, and the High Meadows Environment Institute. L.K. Weber, Gerhard Edlinger, Professor of Energy and the Environment, and also Professor of Psychology and Public Affairs. And finally, at the JRCPPF, Pallavi Nuka, who is the Associate Director, and Nancy Turco, who is the Program Coordinator. So all of these individuals, you can see the diversity in their backgrounds and expertise. They came together to help us put this program together, and I really sincerely want to thank them for their efforts. This conference is also being co-sponsored by centers at Princeton University, and I want to acknowledge their assistance as well. The first is the Center for Policy Research on Energy and Environment at SPIA, and their staff, Keely Swan and Chuck Crosby. The Adlinger Center for Energy and the Environment, and finally, the High Meadows Environmental Institute. The topic of our conference, as is clear from the title, is climate change, a challenge that all of us are facing globally, and what we need to do about that. One of the core objectives that has come out of the various conversations around the world on climate change is this goal of net zero by 2050. So we are going to use that as the pivot to have that deep conversation about what to do about climate change and how best we can globally coordinate on this very important question that is of consequence for all of us. So we will be talking about why net zero by 2050 is important from a science perspective, and then we will get into the questions of how we can get there, how to make it happen, and the various angles associated with it. So without further ado, let me go to our first panel and introduce my colleague and the moderator for the first panel, Michael Oppenheimer, who will take it from here. Michael, over to you, please.
Thank you, Atif. This panel is Why Net Zero 2050? Achieving the goal of net zero emissions of greenhouse gases, particularly carbon dioxide, by 2050 has become a global benchmark of success for international cooperation aimed at grappling with climate change. It's also become a benchmark for national climate policies put forward by, among other governments, the Biden administration. Net Zero 2050 attained prominence after the Paris Agreement of 2015 called for the world to restrain global emissions to well below 2 degrees Celsius above pre-industrial levels, while making best efforts to restrain warming to, in fact, less than 1.5 degrees. It provides a key marker of potential success on the road to achieving the Paris objectives. In this panel, we aim to explain how these objectives emerge from both climate science and an assessment of how fast emissions can be reduced in a practical sense. The first two speakers are at this moment participating as authors of the latest report of the Intergovernmental Panel on Climate Change to be released on Monday. They're both deeply involved in the discussion over wording of the summary for policymakers of that report, and we're lucky to have them agree to appear here today nevertheless. Their comments will not cite specifics in that report, and thereby they will not compromise the embargo on the report. Let me just go down in a row on the speakers. I point you to the conference website for their full bios. Zelina, Zaiton, Ibrahim is a coordinating lead author of the integrative chapter of that IPCC report and will give us a global perspective on impacts of climate change. Kris is an author of the IPCC chapter on health, well-being, and the changing structure of communities, and will particularize those impacts by reaching from the global to the local level. Detlef and Vuuren will give us an overview of greenhouse gas emissions pathways that may achieve the Paris temperature targets, and Clarke will explain some of the implications of those pathways at the sectoral level. And those hopefully will hook in well with the next panel. As I said, their bios are available on the website. Each speaker will have 15 minutes, leaving about 10 minutes at the end for questions. Please put your questions in the question box. So let me turn it first over to Zelina.
Hi, thank you very much, Michael, and thank you very much for inviting me to participate in this conference. I think it's very important to be able to communicate what we're doing and also what the concerns we have are. And so if you give me permission, I'll just share my screen.
By the way, Zelina, let me say, and this to all the speakers, I'll give everybody a 3-minute warning.
Okay, great. Yeah, that'll remind me. So thank you very much. So to my topic today is to explain a little bit about the climate change risk, how we're doing the assessment, and what has been happening so far in the assessments and the reports with IPCC and the assessments that have been done previously. Probably some of you are familiar or have heard about the 6th assessment report, which came out last year from Working Group 1. And this is giving the underpinning science or the physical science of why climate change is happening, what are the main factors, and what to anticipate in the future. And this was released in August 2021. The main conclusions from this report is that human influence has warmed the climate at a rate which is unprecedented, in the last 2,000 years. And you can see from these two graphs, and especially we are now on the right-hand side of the graph, the observations that have been made and what are some of the simulated, if you compare between without humans and with humans, it's very clear the causal factor here is our presence on this earth. And we find that from the report, the CO2 concentration is the highest in at least 2 million years, sea level rise is the fastest rates, and the Arctic sea ice area is the lowest level in at least 1,000 years, and glacial retreat is unprecedented in the last 2,000 years. Future emissions will cause future additional warming. And here we see the latest scenarios which have been presented. And if you look on the right-hand side of the panel, I think this is the thing that's very interesting, very relevant for the issue of why net zero 2050. If we look from the top here, we're doing a simulation of what the global warming temperature, and this is 0 to 5 degrees centigrade, and this is relative to pre-industrial temperatures. So we are here at pre-industrial at 0, and where are we now? You can take a look further down as we will see, but look at where the CO2 emission levels are. If we're looking very low, and we're around here, and take a look at the temperature scale, low CO2 emissions, intermediate, high scenario, and a very high scenario of CO2 emissions. So this is coming from the Working Group 1 figure, SPM 8. That's a summary for policymakers, and that's the text that has been simplified and summarized in order to be able to give the key messages. The main to understand, to internalize, is that with every additional amount of global warming, the changes that we expect to see will get larger. And this is just some visualization of what would happen at 1.5 degrees centigrade, Paris Agreement, 2 degrees centigrade, well, the upper limit of the Paris Agreement, and at 4 degrees centigrade. But these are average temperatures, so you would see that around the globe, different regions would actually be facing higher or slightly lower average temperatures. So what would that mean? Where are we now? Now in where we're just after 2020, here we're in this place here, and if you take a look at this temperature, we're well above 1. In fact, in the last 10 years, the average is our temperature now is at 1.09 degrees centigrade. And in the last year, the World Meteorological Organization estimated that the average temperature was 1.2 degrees centigrade, and that's coming very close to the 1.5 target of the Paris Agreement. But if we look at the different scenarios, and here I've outlined the very low CO2 emissions, this is the only scenario. That means in terms of how much emissions will come out, bearing the population, and if we are very sustainable in the way in which we do things, that's the only scenario which is consistent with meeting the Paris Agreement target of 1.5 degrees centigrade. And that also is consistent with a net zero 2050 that would be needed in order to try and achieve this target. So unless there are immediate, rapid, and large-scale reductions in the GHG emissions, we will have very strong concerns about being able to limit warming to 1.5. And some of the things which really are very worrying from the report Working Group 1, and for me, it's also very relevant. I live in a country which has been always a hot temperature, almost all year round. And, when I was younger, I would say, well, weather is not really very interesting for me because it's either wet or wetter. It's hot, or might be hotter and a little bit cooler. There's not really much change. And you expect rain almost every day. There's not much variation in the weather that we're getting. But from this report, we see that projected changes in extremes will be larger in frequency and intensity. And in my country also, we're starting to see that. 10-year events and 50-year events. So if you're looking at these diagrams here, you will see that at the let's say range of temperature, we're at the present 1 degree centigrade, hot temperature events, a 10-year event would occur 2.8 times more likely compared to what it was in the pre-industrial 1850 to 1900. That's very worrying. But if you look at the 50-year event, that increase in now is actually 4.8 times what was seen before. And for rainfall, which is relevant to my situation in Malaysia, projected changes in heavy precipitation doesn't show that great a change in likelihood, but it's still increased from what it was before, 1.3 times. But of course, this is just the average for the global level. Different regions will experience different types of changes, and especially formulation, from what I see, we're starting to see these extremes occurring more than we have had before. But the biggest problem for many developing countries is that the period of record is very short. So we don't have the level of certainty or of confidence in what is what the return periods are and what these changes are anticipated to mean. The main thing is from the Working Group 1 report, and that's very concerning, is that extremes are more frequent warming. And the trends that we have now mean long-term changes. And in particular, this is related to sea level rise. The warming we have today means that sea level rise, which is a much slower response, will occur over decades and centuries and is unavoidable. And if we just look under the low CO2 emission scenario, not the lowest, not the one that meets the Paris Agreement, the second lowest, we're looking at 0.5 to maybe a 3 point something meter rise in the sea level that's being projected. So what risk can we expect with all of this physical science, these physical changes and climate hazards which are happening? Well, at the global level, the assessment of risk is based on a framework which was developed quite some time ago. So the framework of assessment of risk and its portrayal in simple diagrams have been developed now using expert judgment and based on available information about climate impacts. In the last assessment report of the special report on climate change and land, we've seen great advances being made in how this assessment is being made. See the flow of methodology, looking at the literature, developing the protocol, doing expert elicitation, doing several rounds, and in the special report, 3 rounds of assessment and discussions were carried out in order to develop a figure which you will see on the right-hand side. And this is very much like a traffic light, vertical bar, where we have undetectable risk occurring and moving, and the colors will transition up. Moderate risk with a yellow color, high risk at red, and to very high. And you see the descriptors for these risks, and white meaning that it's very difficult for us to detect the changes. It doesn't mean that the change is not occurring. It just means that there's a lot of noise. And weather, of course, if you're very seasonal, there's a lot of noise. So we can't distinguish the change that's happening from the noise that's happening in the background. But when we move into yellow, we start to detect these risks. And when it goes to red, it becomes severe and widespread. But purple indicates the possibility of irreversibility, maybe tipping points in some areas or some sectors, combined with our limited ability to adapt to the changes which are taking place. These risks at the global level are aggregated into 5 reasons for concern. So RFC1 is a concern about unique and ecosystems. RFC2 is on extreme weather events. RFC3 is on the distribution of impacts around the globe. That means that different people might feel these risks differently. And we expect that most vulnerable or most exposed people will be at greater risk than those who are not so exposed. So what is the difference in this, distribution? And what would be the global aggregate impacts, RFC4? These are impacts to the ecological system and including monetization of these impacts. And RFC5 are large-scale single events, global level type of events, ice sheets melting, ocean circulation being changed, because we have been starting to see some of these signals becoming more worrying in the last few years. So what has the assessment shown us in previous reports? This is coming from the special report from 1.5. Yeah, fine, thank you. This is coming from the special report for 1.5. And you can see these color bars with, of course, RFC1, which is unique and threatened systems, showing a much redder color compared to the other reasons for concern. But let's take stock of what has happened in the different assessment cycles of the IPCC. And this has been presented in a very recent paper by Zommers, which uses this improved assessment methodology. And we are looking here at a set of 4 what we call burning embers, or 4 diagrams of risk assessment. And we're moving from the 3rd assessment report Dr. Smith in 2009, 5, and the special report in 1.5, and take a look at how these colors are changing. You can see this dotted line showing where the risk levels from, let's say, previously here at a higher global warming level are now expected, the same level of risk is expected to occur at much lower temperatures on this big drop that you see here. And this is for first 3 RFCs. And similarly, we're seeing this type of drop where the risk with becoming severe will be at lower levels. And especially for the large scale discontinuities, I was saying the RFC 5, in the last few years, we are starting to see, it's very worrying. You see this drop is much steeper than for the other RFCs. So what's next? Well, as Michael mentioned, Working Group 2 is now in discussion, and we expect the results to come out next week. So I hope you will put your ear to the ground and, be cognizant of how these changes would occur. You might actually try to anticipate from the embers, because similar set of embers will also have been developed. And so you can try to anticipate based on the figures just now where we might be in the future. So with that, thank you very much for listening. I'm just ending with a picture of an extreme flood we had in Malaysia in 2014. This flood was estimated to be a 1 in 200 year flood. Of course, our records are only about 60 years. So you can imagine what the statistical concerns are in trying to estimate what type of extremes we're facing now. Thank you very much.
Thank you, Zaiton. Next will be Kris Ibrahim.
Thank you very much, Michael. Really appreciate the opportunity to talk with everyone today. And thank you, Zelina, for a really excellent presentation. Really appreciated all of your comments. I'm going to talk about why net zero from the health perspective, building off some of the comments from Zelina. I want to start with the diagram on the left. Across the top, it shows you some of the factors that are changing in our changing climate. Importantly, when we think about health and some of the other sectors, those changes interact with a wide range of demographic, socioeconomic, environmental, and other factors. And together, these hazards created by our changing climate, changing in exposures, changing in underlying vulnerabilities, and changing capacities of systems to manage, then determine the risks that we'll be facing in the future. Those interactions affect a range of exposure pathways that are typical when we look at health outcomes. And you can see a long list across the bottom. And this is not a complete list of all the climate sensitive health outcomes. I've had the privilege of working in many low and middle income countries, and these are all of the kinds of issues that ministries need to deal with. Climate change is a cross-cutting issue. It cuts across the issues within ministries and is not easily stovepiped into a program for vector-borne diseases, for example. The photograph on the right is just a reminder when we look at the health risks of a changing climate, the estimate is about 85% of those risks are in children. In the United States, when you say climate change, people tend to think about polar bears. Polar bears indeed are at great risk. Children also are at great risk. I wanted to talk about a couple of advances that help the discussion along the net zero pathway. The first is there's been increasing emphasis in the health sector to conduct what are called detection and attribution studies. These are studies that determine the extent to which climate change is influencing particular health outcomes, generally in events. We haven't really done this yet for changes in the geographic range, for example, of a variety of infectious diseases. These are two examples of recent detection and attribution studies on heat-related mortality. The figure on the left is a study that looked at 43 countries around the world, and then using work that is coming out of Working Group 1 on detection and attribution for heat, combined that with a massive data set that this group has and looked at the proportion of heat-related mortality over recent decades, varies from country to country, of how many of those deaths could be attributable to climate change. And the answer across these countries is about 37% of heat-related mortality could be attributed to climate change. The map on the right is from the heat dome that hit the Pacific Northwest and British Columbia in Canada at the end of June of last year. You can see that temperature records in the Pacific Northwest were broken by more than 10 degrees. For those of you who tend to follow your local meteorologist, you know it's much more typical to break records by tenths of degrees. It's almost unprecedented to see 10 degrees. A detection and attribution study concluded that this event was virtually impossible without climate change. Across the major regions, Oregon, Washington, and British Columbia, current estimates are more than 1,000 excess deaths. Over the course of an event that lasted 3 to 4 days, we're talking about 1,000 people who died, who would not have died otherwise. We're starting to quantify how many people are already dying from climate change. Another advance follows on the remarks from Zelina of looking at what we all call in the field the burning embers. As opposed to what Zelina described of using expert judgment, a group of us got together and looked at all of the projections that had been published on what the risks could be for health in a changing climate. And we synthesized the evidence from the literature. There was only sufficient literature for 6 health outcomes. You can see heat-related morbidity and mortality, ozone, malaria, dengue, and other diseases carried by Aedes mosquitoes, Lyme disease, and West Nile. The color schemes are the same as what you heard from Zelina. The 0 line is pre-industrial. You can see the increase in global mean surface temperature up the left. We know from the Working Group 1 report that Zelina referenced that when we look at net zero, we're looking at trying to achieve temperatures around 1.5. And you can see how close those risks are coming to us. She showed you how significant the risks are, and these are the risks for health. We took this one step further. We used the shared socioeconomic pathways. These are pathways of possible development over the course of the century without taking into account climate change to the extent possible. And using these shared socioeconomic pathways, we developed 3 scenarios for adaptation. The embers on the left are a world in which there's very high challenges to adaptation, high challenges to mitigation, and very low progress on adaptation. The ember in the middle is when there's medium challenges to adaptation, medium challenges to mitigation. And we make progress with adaptation, but not as fast as we should. It doesn't keep pace with climate change. The ember on the right is a world with low challenges to adaptation, low challenges to mitigation, and where the world really aims for sustainable development. As you look across these 6 sets of embers, you can see immediately the risk increasing with temperature, but also our development choices really matter. What we do with mitigation, what we do with adaptation is going to be critical to the health risks that we're going to be facing in coming decades. And those embers don't include all of the health risks. And I'll highlight here just one. There's been a number of field experiments of concentrations of carbon dioxide in the atmosphere expected towards the end of the century. And what happens to wheat and rice when they're grown in those conditions? And this summarizes briefly what was found in these experiments, that carbon dioxide does promote plant growth, particularly in wheat, rice, and related kinds of plants. But as those plants grow faster, the plants have more carbohydrates in them, and they've got less protein and essential micronutrients. So in essence, you're seeing under higher CO2 a real decline in the nutrient density of our food. This is separate from climate change per se in changing temperatures and changing extremes. And I'm putting this up here because the impacts are so large. Currently, there's about 800 million people in the world who are food insecure. They don't get enough to eat. There's about 2 billion people in the world who don't have sufficient micronutrients. The numbers are very large. One study of looking just at the poorest rice-dependent countries in the world concluded that at CO2 concentrations later in the century, we're talking about 600 million people could be affected. Incredibly large numbers. On the right is just one example. It was a modeling study that looked at temperature and carbon dioxide change, looked at positive influences like changing in our markets, the negative influence of carbon dioxide. And you can see the conclusion of this decrease in the global availability. Sorry about that, my mouse likes to move before I like to move it. Decrease in protein, iron, and zinc by very large amounts. So we know we're not capturing sufficiently the health risks. Moving on, I'd like to emphasize a couple of other points. One is on mitigation per se, and we're going to hear some great talks on mitigation. And the piece I would like to bring to the table is that when you look at the mitigation policies and technologies, almost all of them have significant benefits for health. And I'll show you a couple of studies that when you start quantifying the number of avoided hospitalizations, the avoided premature deaths, and value those, the value of the health benefits of mitigation are about the same size as the cost of mitigation. We should be mitigating for our health. First example, electricity generation. There's lots of ways that electricity generation affects morbidity and mortality. This is a recent study looking at the Paris Agreement, specifically looking at the nationally determined contributions under the Paris Agreement, and looked for 9 countries, the number of deaths that could be avoided by reductions in exposure to particulate matter from the sectors that are listed in the top right for 2 different scenarios. One is where the world is aiming to sustainable development. The other is, in addition to that, there's a health in all policy approach to make sure that we not just aim to sustainable development, but every action we take, we ensure that we protect and promote human health and well-being at the same time. And you can see very large numbers of avoided deaths. You value those deaths, again, the value of the benefits to our health are greater than the cost of implementing the mitigation options. I've got a couple other examples. This is from the Northeast in the US, from the Regional Greenhouse Gas Initiative. The left is a cartoon that shows you a little bit about how the study was done. On the right, this study focused only at child health outcomes and how they could be benefited by reduced exposure to air pollution and valued those economic benefits. The map on the right shows you the cumulative benefits over 6 years, and in some places those benefits were $1 million to over $21 million. Very large benefits. Again, these would more than offset the cost of mitigation and would significantly benefit the health of children. Studies are also being done at much finer scales. Here's one that was done in Wisconsin, looking at the health benefits of clean energy. You can see the numbers: creates jobs, increases the state GDP, reduces greenhouse gas emissions, and they estimated about $21 billion in health benefits from reducing exposure to air pollution. Transportation is another area where there's lots of opportunities for reducing our emission and increasing our health by getting people to walk and bike more than driving vehicles, for example. This is one example from Stockholm of looking at promoting bicycling as active transport. And you can see the numbers on the right that the fall in chronic disease cases by getting more people biking was estimated to save over 560 million euros.
3 minutes, Kris.
Thank you, Michael. And moving on to the other issue, adaptation, there is lots of work being done in health to try to adapt to a changing climate. And I'll show you in a moment, not anywhere near as much as needs to be done. This is the framing that's being used by the World Health Organization and therefore being used by ministries of health around the world in looking at the different elements of health systems that need to be strengthened to be able to prepare for and adapt to further climate change. There is an annual survey from the World Health Organization looking at how countries are doing. The numbers were reported late in the fall. And you can see that just 91 countries reported, and of those, about half have national health and climate change strategies in place, but very few have high or very high levels of implementation. The real challenge is the lack of funding. When you look at the multilateral funds for adaptation, less than 0.5% is going to health. Sort of same message when you look at how much research is going into climate change and health. Tiny, tiny, tiny fractions of what is being spent in other sectors. And this is an area where we need significant improvements in our investments if we're going to make a real difference in protecting and promoting our health and ensuring that we are on a pathway to net zero for 2050. Thank you very much, and I look forward to the discussions.
Thank you, Kris. Thank you for an excellent presentation. I think you and Zelina together have set us up very well for Detlef and Leon to explain the pathway to maintain a safe climate and if it's really possible. Detlef, over to you.
Yes, thank you. And I hope you can see my screen.
Yes.
Okay, great. So I would like to start my presentation with the Paris Agreement. And in the Paris Agreement, the world has agreed to keep temperature well below 2 degrees and preferably even 1.5 degrees. And in another article, it says that parties should aim at reach global peaking of greenhouse gas emissions and in the second half of the century, reach a balance between anthropogenic emissions by sources and removals of sinks. But what does it mean exactly, and why is this formulated in this way? I would like to show that in the presentation. But to answer that, you have to go through this very complex cycle of causal relationship for climate change, which we heard about impacts at the end, but then you also have to understand the climate change itself, how it relates to greenhouse gas concentrations and emissions, and ultimately how it relates to human activities like energy and land use. Now, to understand that, we have developed computer models, and one set of those models looks into the relationships between emissions and climate change, which are these complex climate models. We have other models that can look into impacts that were presented in the previous presentations, and we have models that can relate human activities to emissions. Now, looking at the first set, these emissions and models the models that look into climate change itself, and we can nicely summarize them actually by a single graph that was also published by the IPCC, which relates the cumulative CO2 emissions, that's the total amount of CO2 we put into the atmosphere, to the temperature increase. And what you see when you plot the outcomes of these models is actually that a nice linear relationship emerges. There's uncertainty. We have models that are more sensitive. They are on the upper side of these pink cloud. And we have models that are less sensitive, which would be on the lower side. But at the same time, there's a very clear relationship. What we can now do is look into projections of CO2 emissions. And so historically, CO2 emissions globally have been increasing over the last decades. And if we assume that they would increase at a similar rate, then we would emit about 4,000 to 5,000 gigatons of CO2. We can use this graph to estimate easily what the temperature consequence would be. And we simply add this to the current emissions, and we can see that in that case, we would end up with a global increase of temperature, but somewhere between 3 and 5 degrees. Now, we have seen in the previous presentations that you end up far into the red areas of these burning embers. And so it's the world that we try to avoid. which is also agreed in the Paris Agreement. In the Paris Agreement, we said we would like to stay well below 2 degrees and preferably 1.5 degrees. And we can use now the same graph to estimate how much emissions we can still emit. And so for well below 2 degrees, this would be around 1,000 gigatons of CO2. But we have to solve first the problem, where are we going to read this graph? Are we going to believe the most sensitive models or the least sensitive models? Do we read this graph at the left side or the right side of the pink plume? Yeah, as scientists, there is some agreement that we more or less do it with 1/3 of the models on the left and 2/3 on the models of the right, so that you at least have a 66% chance of meeting the target. And in that case, as I said, therefore well below 2, you end up somewhere with 1,000 gigatons of CO2 that you could still emit from 2020 onwards, and for 1.5, around 400 gigatons of CO2. Now we can do now some very simple illustrative calculations of what that would mean. And so we take this 1,000 gigatons of CO2, and if you would go linearly from today to net zero, it would mean that you still have 45 years of emissions, because it's 1,000 gigatons of CO2. We emit at the moment 42 gigatons of CO2 every single year. Yeah, 45 years would mean that somewhere after 2060, you have to be at net zero for CO2. Now, 45 years is not a lot, and most of the investments that in the infrastructure we build is intended to last at least 40 years. And so more or less, it would mean that from today onwards, globally, you only want to build new infrastructure that doesn't emit CO2. But for well below 2 degrees, the situation is even much more dire. That would mean that you have to end up at net zero in about 18 years if you follow this linear line. Now, we already know that in existing infrastructure alone, if you simply let that reach its end of its normal lifetime, the emissions would be 650 gigatons of CO2, and there's another 200 gigatons of CO2 in infrastructure being planned. And so clearly for 1.5 degrees, we already can easily see that reaching that goal means also prematurely retiring existing infrastructure. But this is our simple calculations. In reality, there's a little bit more options. And one of them is that we can have negative emissions. It's possible to take CO2 from the atmosphere, partly by afforestation, possibly by bioenergy in combination with CCS, and there are a few other options. But these options are not unlimited. There are serious limits here. First of all, because if you do a strategy like that, you will temporarily overshoot the temperature target and will be confronted with some of the impacts. But also, many of these options, like reforestations, need land. And so there are possible negative impacts of using land, and it also limits the potential. Now, we more or less estimate that it is possible to have a few hundred gigatons of negative emissions. That's important, and it can really make a difference. But taking that 4,000 to 5,000 gigatons of CO2 that could be emitted under a baseline scenario, and the 400 to 1,000 gigatons of CO2 that you need to reach these targets, you can already easily see that the main story is getting rid of positive emissions. And this negative emissions can only be a side story, making the target in the end possible. Now I'm doing this so far with drawing some simple lines, but in reality, we can also use computer models to do this. These models describe future land use, future energy systems, and they can do some calculations of possible cost-optimal pathways to meet these goals as an heuristic to learn of attractive and possible pathways to reach goals. And then you can, you play in these models with the distribution of your action in time, the amount of negative emissions, but also the emphasis on non-CO2 emissions versus CO2 emission reduction. And what comes out of these models is then these kind of things. What I'm showing here is when do the scenarios reach net zero? And then in the scenarios, you see that for well below 2, this is somewhere in the around the 2060 to 2080. The little black diamond is actually the linear line that I showed earlier. And so for CO2, around 2060 to 2080 for well below 2, and around 2035 to 2060 for 1.5 degrees with an average on 2050. And so that's where this 2050 net target emerges from. For greenhouse gas emissions, it's slightly later than the CO2 target. And so the net zero target is an interpretation of Paris. It's not 100% coupled to the temperature, but it sets a very clear point at the horizon, partly because you can start planning your energy infrastructure with this target in mind. You can play the same game with the 2030 emissions. You can look at all the scenarios published in the literature and then see when in 2030 you have to be. And that's more or less, you have to reduce emissions by about 1/3 for well below 2 degrees in 2030. And you need more or less half them for the 1.5 degree target globally. But how do we get there? So how do we really make sure that these how do energy systems or land use systems look like that achieve these targets? Again, we will be using the models, but then in a reverse mode. We start with the emission targets and then have the models optimizing some form of system or exploring different systems of energy and land use. I can do this in the next graphs. And so I start first with a scenario that is simply a baseline, so without climate policy, and that's projected here. And so you see a slow increase in emissions in line with the historical increase. You can also see that most of the CO2 emissions or the CO2 equivalent emissions or the greenhouse gas emissions actually emerge from the energy sector in blue. The non-CO2 gases are a major source indicated in gray. And then we have globally the industry sector, dark red, and transport in yellow. Buildings is shown to be much smaller, but please note that here the emissions associated with electricity use in buildings are shown here as part of being the energy sector. Yeah, and then you can also, for that same scenario, look into the global energy use. And to make it a little bit simpler, I would like to concentrate only on 2050 and 2100. So this is the same data, but now shown as bar charts. And then I can look into scenarios that meet the 1.5 degree goal. And so first of all, I run the models, I allow every option to be taken, and I assume in this particular case that there's a lot of development also for carbon capture and storage. It's widely available, and this is a possible outcome. So this scenario achieves the 1.5 degree goal, and you can see that it's partly achieving that by a lot of negative emissions. So you see some remaining positive emissions on the upper side. It's heavily reduced, and it's partly compensated for by a lot of negative emissions. But there are different strategies. I can also in the model be more optimistic about the development for renewables in line with what happened in the last few years, or be much more optimistic on demand changes and also run those. And so I can use models to explore different possible routes towards achieving the 1.5 degree target. Now, one thing that I should notice is that in the end, all the scenarios need some amount of negative emissions, which is not so strange because it's almost impossible to bring the greenhouse gas, the non-CO2 greenhouse gases to zero. And so therefore some compensation with negative emissions is always needed to reach net zero.
3 minutes, Detlef.
Yes, that's fine. So if you are looking at this a little bit from a distance and see what is more or less the same in all these scenarios. So first of all, limiting demand is a very important part of the strategy. Then benefiting from the rapid technology development for renewables means that renewable energy is always also part of an attractive strategy. That also means that if it is relatively easy to decarbonize the electricity system, that electrification is an attractive part. Then it's also, you probably can't build an energy system with 100% renewables. So there needs to be some other options there as well, which could be more attention to system integration, CCS, bioenergy, possibly nuclear. And on the end-use sectors, possibly electrification is not possible for everything. So there's other options needed there as well, which could be hydrogen or CCS or bioenergy again. I already indicated that the negative emission side is important. So reforestation is a logical part of this story as well, and development of negative emissions options. We will have to reduce the non-CO2 emissions, but that is not so easy. And so there are technologies to do so, but as long as we eat meat, and there will be still methane emissions associated with animal husbandry, which means that among the lifestyle changes, diet change might be one of the most attractive ones, reducing especially a major source of remaining emissions. Yeah, we can not only calculate the energy consequences, but also the consequences for cost. And we see that in these mitigation scenarios, cost will go up, the amount of investments. And so it goes from 1.6% to 2% into the future. But that's not the most important thing. The most important thing is that the portfolio of investments completely changes. And from a scenario where mostly we have fossil investments in fossil to a scenario where we have a lot of investments in renewables, efficiency, and net integration. I would like to spend the last minute, I hope, on what is the progress so far. And so this is the scenario that I've been showing before, the well below 2 and the 1.5 degree scenario contrasted with the current policy scenario. And now focusing in on 2030, these are the same scenarios. And I'm also now showing a scenario without climate policy in gray, the current policies and the NDCs, and then the well below 2 and 1.5 degree scenario. For well below 2, we need a 40% emission reduction. For 1.5, a 60% emission reduction. And so what are current policies doing? The NDCs, that's the promises of the countries in the world, would reduce emissions around 17%, while current policies are reducing emissions by around 9%. And so basically, we are not promising enough yet at country levels, and we're not implementing what we are promising. That's the situation a year ago, in the beginning of 2021. By Glasgow, the hope was that it would have been changed significantly. In reality, we have maybe gained a few percentage points, but really didn't change this picture in a major way. So the carbon budget is more or less almost depleted. We are not reducing the emissions a lot at the moment still, but there are also some signs of hope. And a few of those are the technology breakthroughs, the net zero targets that are formulated now by many countries, and also the changes, for instance, happening in the financial sector. So I think there is also signs of things changes. Thank you very much.
Very good. Thank you, Detlef. And I should mention that Detlef is involved with the third section of the upcoming IPCC report that's rolled out by 3 working groups and has a serious month or so of work to do following on this. Now, Leon Clarke, please take us away to the perfect merging with the next panel.
Hopefully you can hear me and I'm showing the right screen. So yes, I'll try and do that. So I'm going to build on Detlef's, kind of take off from where Detlef was. I mean, first, actually, I should say thanks for the opportunity to be here. This is great. I've already learned a lot, and I'm excited to be part of this panel and this meeting. In terms of where I'm going to go, so I'm going to, like I said, just take off from where Detlef was, and I'm going to focus on just a set of particular implications. So it's sort of a selected set of issues that are important when we're thinking about what net zero means. I'll focus a little bit on the energy system more so, but try and be a little bit broader for that. And I've tried to pick out ones that I think might be relevant in the context of, say, finance and investment. So to start, let's see if I can get this set up. So first, let me just take off from where Detlef was. So Detlef showed a slide that gave you a sense of some of the dynamics or some of the factors or changes that we're going to see as we think about mitigation, as we think about net zero. Here's a set that are focused just on the energy system. So I'm not talking about land use, although I'll come back to that in a moment. But it's a lot of this, the sorts of issues that we've seen before. Less fossil fuels for sure, zero or negative emissions from electricity, as Detlef noted, electrification, use of alternative fuels, efficiency, integrated approaches, carbon dioxide removal. I'll come back to many of those in the slides that come. I just want to highlight briefly the last slide, though, which gets a little bit at some of the issues Detlef was talking about near the end about lifestyle change and so forth. We're going to see a lot of physical system changes, assuming we go to net zero, that is. If we do that, we're going to see a lot of physical system changes. But along with those come a wide range of societal and institutional changes. And I'll try and highlight those as we go. But I think it's really important not to see net zero, the path to net zero, the change that's involved with net zero is purely a physical one, but also one that's going to require changes in governments and governance and institutions and behavior and so forth. So let me start through some of these examples. So the first one I want to touch on is something that Detlef discussed, which is the need for negative emissions, so carbon dioxide removal. And in the next slide, I'll just discuss briefly the need for it again and reinforce what Detlef said. And I think it's really quite critical to think about. So, but first I want to just note, what is carbon dioxide removal? So, there's a wide variety actually of means for removing carbon from the atmosphere, but generally we can think about them in two broad categories. One of those categories would be those associated with, say, growing forests, sequestering carbon in root systems and so forth. So that's kind of in the category of afforestation, reforestation, soil carbon uptake. That's the land use side. That's the land side. The other side is engineered, we might call engineered carbon dioxide removal. And that we used to think about it broadly in the modeling community as bioenergy with CCS. You grow bioenergy, you burn it, you pump the CO2 underground. Now there's a lot more work going into direct air capture, but there's also other methods as well. But think about it as those two broad categories. And this diagram is just showing the fact that each of those has their own idiosyncrasies and effects on societal and other factors. There's two broad categories. So now let's return again to the need for CDR. So often CDR is discussed in the need to have negative emissions in the second half of the century. I just want to talk about net zero, just net zero. Okay. So this is a figure from the US long-term strategy, which was just rolled out before the last COP. And it shows emissions getting down to zero in 2050. This is for the US. And I want to highlight that you can see both of the means of CDR here. So you can see what's called CDR, and then which is going down below zero. That's the sort of darker lines below zero. And then green is the land use sink. And the ranges are because there's a number of scenarios. So there's two reasons that we need to have CDR even for net zero. One is there are some sectors where it's difficult to remove the emissions. So for example, air travel can be difficult. So in those cases, it's more cost effective to actually use CDR than it is to try and remove the carbon from those sectors. But also, as Detlef noted, actually, before finishing that, I should say that's why you still see some, quote, CO2 in this figure in 2050, even at net zero. But as Detlef noted, once people start thinking not just about net zero CO2, but net zero greenhouse gases, then you're talking about methane, N2O. And as Detlef said, it's very hard to reduce those down to zero. And so CDR becomes a necessity. So CDR is in fact a necessity for net zero. And I'll talk about some of the implications for that going forward. Institutionally and in governance, you have to think about what would be required to make this happen, because this is not something that just happens by market forces. In some sense, we can think about solar cells getting down to a price where you might want to install them. There is not normally going to be a market reason to apply CDR, and so government institutions are needed, for example, prices on carbon and so forth. Okay, The notion of CDR and land use then points out that terrestrial systems are going to be deeply intertwined with net zero. So there's the land sink, as I just discussed. There's also the need for bioenergy. Both of those will actually put some pressure on land use. Now, they're not the only uses for land. We also use land for food, forest products, ecosystem services, and other issues. But the notion is now all of these are in competition, and our understanding is that there will actually be then, I mean, what we've seen from some analysis is, of course, demand for bioenergy can in fact affect food prices. So this competition actually then raises, again, the need for these institutional dynamics. How do we ensure, for example, that when we protect land in one country, we don't just have what you might call whack-a-mole, and then you see land deforested somewhere else, where someone can be doing producing bioenergy or crops? How do you ensure that land that's put into protection actually stays in protection? How do you ensure that food prices for those who are most needy don't actually rise too rapidly? So a number of institutional needs are going to arise from the intersection of land and net zero. And again, we're talking here about net zero. Okay, so then stepping back, the one thing we kind of know, the thing that defines a lot of meeting of the climate problem and of what net zero means is a reduction in fossil fuels. We're going to use less fossil fuels, okay? And that's the bottom line. Ultimately, that's what the energy system is the biggest source. Over the long haul, we got to get fossil fuels down, particularly, clearly fossil fuels without CCS. So how much do they have to go down? Well, if you look at the literature, it's not consistent between the different fuels. So for coal, it's pretty clear. Without CCS, coal needs to go rapidly. You're talking about getting it down towards zero in decades, as quickly as you can. When you look at something like oil, the story is really actually very uncertain. In some scenarios, you may have a lot of CDR and may actually be able to maintain oil for a longer period of time because it's a great energy carrier. In other scenarios, you don't, and you really need to push it out. We may electrify more quickly. There may be some ways to use hydrogen and electricity in a lot of the circumstances where we would have thought it would have been difficult. And you can see that in this figure. This figure is showing the primary energy from oil, and it's in 2050. But I just want to point out the around zero place where I've highlighted. And the scenarios with very little CCS are in, I guess, orange and reddish tones, and those with CCS are in bluish tones. But you can see there's a wide range of levels of oil that we might be using. Nonetheless, there will be very dramatic changes across the board when it comes to fossil energy. Okay, that of course, as Detlef noted, this need to move out of fossil energy is going to have a lot of implications for stranded assets, for assets. Okay. Detlef showed a similar chart. Let me just dive into this a little bit, and particularly coal is at risk. So what this chart is showing is, let's just first go to the shaded regions. The very dark shaded region is showing the gigawatts, the capacity of coal-fired power that would retire naturally based on existing coal fleets. Okay. So by 2070, it'll all be gone. Then the lightly shaded portion is then including new builds, so planned capacity and so forth. All that new capacity that might come on by 2030, and then it retires more towards 2080. The green and blue lines then are showing what's required to limit temperature change to 1.5 degrees or 2 degrees. And what you can see is an obvious inconsistency between those lines and the shaded regions. So what we're going to find is that, in fact, if we build no new coal, we're going to be retiring capital. But the more we build, the more we would have to retire to limit temperature change to 1.5 or 2 degrees. You could see that as making it harder to reach 1.5 and 2 degrees, or you could see it as, if we are going to reach those levels, we're going to have to retire a bunch of capital. Now, that's just the above ground assets. It's also really important to remember that there are a lot of below ground assets. There's a lot of oil in the ground, gas in the ground, there's coal, and we won't be using a lot of that. And that's actually really important, because there's communities, that are dependent on the income from those resources. There's countries whose fiscal balances are heavily dependent on the revenues from those resources, and trying to figure out how to handle those, how to handle the just transitions, and how to handle the sort of more national transitions is a critical element of how we move forward. That leads a little bit into trade. Okay, so we can think about the trade patterns we have today. You think about, in the context of climate and energy, you might think a little bit about fossil fuels. Well, we're going to obviously see very different trade patterns in fossil fuels. If we're not using as much, we're not going to be trading as much. It's as simple as that. And sticking then in the context of fuels that we use in the energy system, we should see increased trade in electricity. That's actually one of the ways that we can use renewable energy in one place and then actually send it somewhere else. So electricity, we should see more integrated electricity systems, potentially with a great deal more long distance transmission. If biomass is a play, we might start seeing trade in biomass. We might be seeing trade in hydrogen or ammonia, carriers of hydrogen. So we might expect to see actually pretty substantial changes in these trade patterns and fuels. But it's not just that. There's also emissions permits. As I noted earlier, we've got to have you've got to have CDR. Well, some countries just don't have a lot of capability for CDR. So if they're trying to get down to net zero, they can't do it without emissions permits. We often think about emissions trading, these trading schemes. We think about it in the near term, at least those of us who do think about it in the near term when we say, well, we know it'd be great to have emissions trading because it makes things more efficient. You can reduce, you can emit where it's, or reduce emissions where it's least expensive, and there's economic efficiency gains to be made, gains through trade. But once you're talking about net zero, it's just it's not just an efficiency game anymore. It's like a physical requirement, because some places are just not going to have the same capabilities for CDR as others. And so this notion of Article 6 and emissions trading, that's going to be a critical part of net zero. And then, of course,
Leon, 2 minutes, 2.5 minutes, let's say.
Okay, 2.5, I'll be there. And then, of course, trade in food, as I discussed earlier. And then it's not just about those, but also technologies. And I think, countries are looking today how to get in the game and ahead in the game on key technologies, batteries, solar cells, and so forth. And then there will be the materials underneath them. So I think it's really important to understand these broad implications for the way we're going to see trade. And then we're also going to see very big implications for investments. And Detlef touched on this as well. This is a figure from AR5, and it's showing the annual investment in mitigation scenarios for 450 parts per million. We talked a little differently back then, 500 ppm scenarios. The key point here is that, or two key points. One, you can see investments in fossil with CCS go down, investments in renewables, nuclear, efficiency, those are all going up. Second, you can see that a lot of these investments are in non-OECD countries. So as Detlef said, there's the notion of the total amount of investment, but what's also critically important is where does that investment happen, both geographically and the sectors. And those are going to be very different over the coming years. Where are we if we're able to make it down to net zero? So I want to just to leave you with this, to say, I pulled out a number of selected observations that might be relevant for how we think about planning from a business perspective for net zero. And it's very clear there's going to be changes. Some of those are going to have some be positive, some are going to be a bit more negative. We know that. There's no denying sort of that character, but there's also going to be opportunities. And so change always brings opportunities, and change can be pretty positive for those that really are embrace those and challenges, see them ahead of time and are ready for it. And we'll hopefully folks will be ready to embrace them. So I'll leave it at that. And thank you very much.
Thank you, Leon. That was terrific. You closed it out nicely. And by the way, for the audience, I don't want to slight Leon. He is also involved in the next section of the IPCC report. And in fact, like me, he's been a lifer at IPCC, and we're going to have to meet one of these days again and discuss the pluses and minuses of that. So now let's have some questions. maybe a T for Palladio. Somebody could tell me how much time we can really give to questions at this point. Technically, we have 3 minutes left.
Michael, you can probably take a couple of questions. I see that there's one from some fellow panelists. Felix had a question, and also Mar.
Okay. So let me read out Felix's question for Leon. How can you think of high oil scenarios with carbon capture and storage when battery electric cars are outcompeting combustion engine cars already, way before 2025?
Thank you, Felix. That's a good question and not a surprising question from oh, let me turn on my video. From Felix. I mean, I think that's a good point. I think that if you looked at those scenarios, and I think actually Felix knows this, a lot of the scenarios that we've seen over time have been built around expectations around vehicles and around solar cells that have changed over time. So I think if you were to look today, that you would actually see a greater penetration of electric vehicles than you see in, in the chart that I showed. Nonetheless, there's only so many parts of the transportation system that are clearly moving to electric vehicles. We know light duty vehicles are moving that direction. That'll be core to it. But then you get into freight of various distances. You get into shipping, you get into air travel. And so the question is how far you go down that track. But I do think Felix's question is a good one. And I do think that the perceptions are changing as we speak about how far electric vehicles will go and what that'll mean for oil.
And now from Mara Guant, lots of emphasis on CCS and direct capture, which seems to maintain the oil industry in relatively decent business. What percentage of fossil fuels is maintained by 2050 in the model? And the same oil industry will not capture its emissions everywhere, and direct capture won't scale to these levels. The last is an assertion, not a question.
I'm looking, and Detlef can feel free to answer this as well. Let me. Oh, it says I'm mute. Okay, let me see. It just depends. So again, I think when you look at it, coal very seriously down, no question, in almost all scenarios and quickly. Oil, the same kind of discussion we just had and Felix raised. I think there's some questions about that, and you see that oil is something that still can be valuable in that time frame. And then natural gas is very unclear, and it actually could benefit substantially from CDR. But I do think fundamental to all of this is this notion of how institutionally are we really going to be able to put in CDR in the levels that would allow you to make the economic trade-off we see in models. So in models, you say, hey, what's least cost? Okay, you know what? CDR might make a lot of sense, and we could leave some of this oil and gas in the system. But can you really set up the institutions and get the societal will to support doing something that really does not have economic benefits outside of climate? And so I think there is a really legitimate question about the viability of scenarios that are heavily dependent on CDR. I think that's a very legitimate question. I don't know, Detlef, if you want to add anything to that.
I think it was an excellent response already. And yeah, so to some degree, we should also look at these models as explorations of different futures. And obviously, there are also scenarios with much more higher renewable shares based on the rapid development of renewables in the last few years. And there, obviously, the main challenge is how to go to very high levels of integration, where still uncertainty remains. And so for different futures, most of these different futures, there are challenges that to be overcome. And I think we should use these scenarios really to look at the possible challenges and the possible consequences of different routes.
So I'm going to cheat and ask one more question that's in the box. It's a nice way to end this one, I think. How would your analysis change for currently high-emitting countries if you allocate global carbon budgets to countries on an equal per capita basis? Either of you.
I mean, this is a debate. So when you're thinking about, so I'm going to, sorry, so I know we don't have time. I'm just going to say, when we look at allocations, when countries should hit net zero, one way to look at that is on a cost effectiveness criterion. So we look and say, what would be globally most cost effective? That's what the models spit out regularly. But there's also a range of actual real equity considerations. One of them could be per capita, what's fair per capita. Also, who's emitted the most, right? What's the historical responsibility? When you start to look at those, obviously it's going to put dramatically more pressure on the developed countries that are high emitting developed countries, and less so that have lower economic output, because the intensity is just not as high.
Let me check again with our hosts. Pallavi, do we have more time for this? What would you like me to do?
Michael, I think you can take one more question and then wrap it up. Barbara just hopped on, and then we can move into the keynote after one more question.
All right, I'll go back then, and I like this one. What are the biggest, most cost-efficient policy changes we need to push today?
Are we talking about mitigation policies or resilience adaptation policies?
You tell me.
I'm not going to, I'm only going to be able to speak to the mitigation side. I think maybe the other speakers should speak to adaptation and resilience. Look, we've always, the economics profession has loved to speak about carbon prices and carbon, market-based instruments forever. That actually, in some sense, economically would be efficient, but there's a wide variety of reasons why that's difficult to implement, and in some cases might not make sense. I think you should be asking the question of both what's the most efficient and the most politically viable. And what we're seeing now is not just carbon prices. Obviously, we are seeing some of that, but a lot of what's going on is sectoral policies. And that seems to be something that can move forward. There's also policies for innovation, which are always hard to quantify the benefits of those. So yeah, I don't know. That's my that's my answer.
All right, let me then close by asking either Zelina or Kris if they want to take the question of where the spending should go on the adaptation resilience side.
Zelina, did you want to start first, or would you like me to start?
Well, you can start, Kris, and then I'll continue after that.
Much of what's driving current risks, current impacts and current risks, is underlying vulnerabilities. We've got too many people living in vulnerable places. We've got too many marginalized communities. The inequities with climate change are exacerbated. They're exacerbating our current inequities. And focusing on addressing our current inequities and our current vulnerabilities will make us more resilient today. And as we continue those programs and those policies, more resilient in a changing climate. Zelina?
Thank you, Kris. Yes, I agree with you. And I think the other thing is that a lot of action, I know I see from my experience is top down, coming down from governments to people. But I think really we need to try to think how to get each individual to start thinking about when they take an action, how does that action relate to making themselves safer or more resilient to possible changes in climate change. So when they want to buy a house, where is the house? Where is the escape route if something happens? What services are available? Those sort of things. I think in the end, no matter what government measures you have, government cannot be everywhere. I mean, it's each individual having the knowledge and resources and awareness of the possible risks that they might be facing, and looking at the pathways or the resources that might be available, or even asking for these type of resources. But the issue is, as you said, the inequity. People who are most vulnerable don't have access to the resources, aren't aware, maybe don't have the knowledge, don't know where to seek for the knowledge, or they're being marginalized and not being addressed in the adaptation action.
Thank you, Zelina, for that closing note. And please, the audience, join me in electronically, virtually thanking the panel for doing a great job as an opener for the conference.
And thank you, Michael, for your continued leadership.
Thank you.
Thanks.